Okay, so from now on for end behavior, I'm just going to say it out loud just because I'm kind of getting a little tired of writing it because a lot of these problems are now being a little bit redundant. So when looking at the end behavior, again, I look at the degree, notice that it's odd. I look at the leading coefficient, I determine it's positive. Therefore, the end behavior of this graph is going to be falling left, rise right. But now to be able to determine the zeros, that's a little different case. I need to set my function set equal to 0, and now I need to solve for x cubed minus 36x. So to do this, what I need to do now is find the values of x that make this true. Well, I can't just solve for x because I have two of them, and one's to the third power, one's to the first, so I can't combine them. However, I do notice that they have an x in common, so I'm going to factor out that x. And by factoring out that x, I discover something very important, that my negative 36 is a square number, and also my x squared is a square number, and I'm subtracting the two, therefore I have a difference of two squares. Now, you don't have to do it that way. You could rewrite it. You could either do it, you could determine that it's a difference of two squares and say an x times x minus 6 times x plus 6. Or you could actually just use the zero product here and say, well, x equals 0, and then x squared minus 36 equals 0, right? Or you could use the zero product here and say x equals 0, x minus 6 equals 0, or x plus 6 equals 0. Either way, when you solve, what you're going to notice is by here you're going to use the square root method. Here you're just breaking it apart and solving. But what we notice is that x equals 0, x equals 6, and x equals negative 6. And here you'd get the exact same values. The important thing is now determining the multiplicity. And again, I'm not going to write this out. I'm just going to kind of say it. When determining the multiplicity, we need to look at the zeros. And here's a very, very big important point where you can see that the multiplicity, it all depends on the exponent of your factor, all right? So here, I didn't factor this all the way down. Over here I did, and you can see that the exponent of each one of my factors is 1. So all of my zeros have a multiplicity of 1. Now, some students might look at this and say, oh, I see an x squared. That means a multiplicity of 2. That's only the case when you have an exponent of your factor. So therefore, even when I solve for this, I'm going to x equals plus or minus 6. Each one of these multiplicities are going to have a multiplicity of 1, or an odd multiplicity, as we like to say, meaning that my graph is going to cross at each one of these zeros, becoming my x-intercepts. So there you go, ladies and gentlemen. That's how we look at that problem. Thanks.